Hello, my name is Sinan Akkar, and in this first presentation talk, I'm going to give you the essentials of ASP13 ground motion prediction equation, which is developed by using the recent, I would say, pan-European ground motion database. As Vladimir did, I mean, I did not follow, in my presentation, I'm not going to follow the questions raised, but I'm sure that you will find the answers. And I will emphasize them one by one. So I'm going to give you an overview of ASP13 with emphasis on magnitude dependence of sigma. This is one of the questions. Reduction in sigma after 3 seconds, another question. Dependence of residuals on depth, and the normal faulting factors. All right, so these are the major features of ASP13 predictor model. So we used a subset of what we call as resource. It's going to hopefully replace Ambrosses et al. Strong Motion Data Bank, European Strong Motion Data Bank. It uses a subset of resource, and we used a total of 221 earthquakes while developing the predictive model. The total number of records is a little bit over 1,000. We're predicting PGA, PGV, and spectral acceleration, PSA actually, pseudo spectral acceleration between 0.01 seconds to 4 seconds. The horizontal component definition is geometric mean. Based on a previous study by Julian Bommer and myself, we developed a model, actually 3 models, and for the 3 models, and they use different distance metrics, RAP, hypocentral distance, and Joyner and Boer. So the first 2 is a point source distance measures, and the last one is represents the extended source distance metric. The maximum distance is 200 kilometers. The maximum depth is 30 kilometers. Minimum and maximum magnitude values in the database we used is between 4 and 7.6. And the maximum and maximum VS30 values we used is 92 meters per second to 2,165 meters per second. But I would say that this, 2,000 meters per second, it is 2 kilometers. It's, we're not essentially recommending it as part of our recommended VS30 value. So these values actually show us the recommended values of our predictive model. So we're recommending it to use between magnitude 4 and 8, distances up to 200 kilometers, and for VS30 values between 150 meters per second to 1,200 meters per second. Okay, so this is the ground motion, the database we used. So essentially, all the recordings have 3 components. As I told you, we're using data a little bit over 1,000, and we're not making any difference between main shock and aftershock recordings. The focal depth of the entire database is less than 30 kilometers, and all the recordings have measured VS30 values. There is no inferred VS30 value. Well, as you can see from the overall distribution, the database has a uniform, uniform distribution between distances 5 kilometers to 200 kilometers and magnitudes between 4 and 7. Unfortunately, in the European database, we don't have too much large magnitude events. This is another way of representing the strong motion database. Now this time I'm just showing the distribution again in terms of magnitude and distance for different VS30 bins. So this is, I would say, rock, stiff, soft soil, and then this is, I would say, very soft soil. So the database lacks significant amount of data for rock and very soft soil. We are quite in good shape for stiff and soft soils. Again, we don't have too much reverse data from reverse events. Most of the style of faulting is normal and strike slip. normal comes from Italian events, and strike slip comes from Turkish events. And all right, and this is the distribution of data again in terms of depth, magnitude and depth. As you can immediately realize, we have a good distribution of data, depth distribution for magnitudes below 6, and for magnitudes above 6, the depth distribution is limited up to 20 kilometers. All right, so this is the functional form that, of our predictive model. So we have a backbone equation which estimates the median ground motion for reference rock, which is described by VS30 equals 750 meters per second, and then we are adding the nonlinear site model, and then we have, of course, the aleatory variability. So the backbone functional form considers quadratic magnitude scaling with a hinging, and the hinging magnitude is 6.75. We are considering magnitude-dependent geometrical spreading. We tried to add the inelastic term, but we failed we failed in that. We used your approach. We, tried different distance, say, bins, and to come up with the inelastic coefficient, but we couldn't do that. So in that sense, we believe that inelastic attenuation is sort of addressed in this distance term.
Excuse me, Sinan, when you say you couldn't do it, you mean did it come out positive?
The coefficients did not make any sense.
Okay.
Yeah, the coefficients did not make any sense. And this is the nonlinear side term that we used to address the side effects, actually developed by Abdullah Sandıkaya, our colleague, and one of the co-authors of this paper. Okay, so now from this point on, I'll try to address the questions raised by the project members. So in our style of faulting term, we are not considering any Z-Tor term, or in our preliminary analysis showed that the style of faulting term depends significantly on the database distribution. So essentially what we did to come up with some reasonable numbers, reasonable coefficients for style of faulting is we used the subset of our database, and we removed very poorly recorded earthquakes from the subset, and then we derived our normal and reverse style of faulting coefficients. So these are the, say, the normal to strike slip ratio of style of faulting of our model is given with this curve, and this is the reverse to strike slip ratio of our model. Okay, so if you make a comparison of our, say, style of faulting coefficients with the GMPs produced by NGA West 1 project, you would immediately realize that, again, our coefficients, normal to strike slip ratios, fit well with Campbell and Bozorgnia 2008 predictive model, and also eventually they fit well with the Akkar and Bomer 2010 predictive model, which is in a way superseded by this new predictive equation. For reverse to strike slip faulting ratios, there is the comparisons show that the behavior of reverse to strike slip is quite complicated. We don't have a, say, sort of good match with any one of the models compared here. On the other hand, the rest of the models also have quite a bit of difference in terms of estimating the reverse to strike slip ratio. For NGA West 1 models, we used Z-Tor here as 0 in these comparisons. Okay, so these are the residual analysis, and they're showing the overall trend. So the first row here shows the between event residuals, the second row here shows the within event residuals, and this within event residuals in terms of distance, Joyner and Bohr distance, and again the within event residuals in terms of shear wave velocity. Now, as I told you in the beginning of my presentation, the large magnitude events in our database, they are missing. So in that sense, when you just, so a brief explanation here. So again, we divided the, say, residuals into different magnitude, distance, and we have 30 bins. So each dot here shows the average of each bin, and this is the standard deviation above the average. All right, so for magnitude, say, I would say below 7, it seems that there is no dependence on magnitude for residuals. I mean, I wouldn't rely on the, say, statistic given for magnitudes above 7 because, I mean, we have very few data. So in that sense, I would say we don't have, our model doesn't show magnitude dependence for magnitudes below 6.5 or maximum 7. There is no, as you can see here, there is no bias in terms of distance, and for shear wave velocity, we have 30. Well, again, for peak run acceleration and for spectral ordinate at 1 second, we don't show too much bias, but for very short periods like 0.2 second, we have some sort of bias. The model tends to overestimate for softer sites. Okay. A similar plot. Again, I'm showing the, say, the standard deviation of the residuals. Okay, the standard deviation of the residuals for between event. The first row shows the between events, and then the second row shows the within event residuals, so the standard deviation of the residuals, again, for different bins, all right, and in terms of magnitude here, okay? So again, as you can see here, the standard deviation shows a stable, say, variation for magnitudes up to 6.5, and for these statistics, I mean, they can mislead you because the number of data is so small for magnitudes above 6.5 or 7 that these variations would mislead you. Essentially, what I'm trying to tell again is that there is no magnitude dependence of our sigma for magnitudes, say, up to 6.5. Now, because I know that for this project the style of faulting is an important parameter, I'm repeating the same type of, say, analysis, residual analysis, but this time breaking the standard deviations into normal, reverse, and strike slip. So the first column shows the normal between event residuals. The second column is the reverse. The third column is the strike slip. And again, the first row shows the variation of standard between event residuals for PGA. The second column is 0.2 seconds, and the third column is 1 second. And again, as you can see here, for normal and for strike slip style of faulting, the variation of between event residuals for different magnitude bins do not show a significant say dependence on MW. Of course, it is valid for magnitudes up to 7, but for for reverse style of faulting, we do have some sort of trend in terms of magnitude. So again, this shows us that, to me, our estimations are in good shape for strike slip and normal style of faulting, whereas for reverse events, because the database is not sufficient, does not cover sufficient reverse events, our estimations might be biased. Okay, so these plots again show the modeling uncertainty in terms of magnitude and style of faulting. We used the expressions proposed in Al-Atik Young's peer report. So first row shows the PJ values, the second row shows 0.2 seconds, the third row shows 1 second. And the first column again, strike slip, second column normal, and the third column is reverse. I mean, I know that the legions are very small. I'll try to describe them to you. So this one here shows a sigma mu for magnitude 6, and then this is for magnitude. So excuse me, this is for magnitude 8. This is for magnitude 7.5, and no, this is for magnitude 7.5. And this black curve is for magnitude 4, all right? And what you observe is, well, in a general sense, for strike slip and normal, the behavior of sigma mu is quite similar. For reverse, there's a little bit, it's a little bit higher. It's a little bit higher. And the modeling uncertainty is significant for, say, magnitudes 8, 7.5, and magnitude 4, all right? They do not show a significant variation for magnitudes 4.5 and I would say 6 strictly, I would say between 4 and 6. And with some sort of tolerance, I can also say that the modeling uncertainty doesn't change significantly for magnitudes up to 7, because this band is, I mean, more or less the same variation. And this is valid for PJ 0.2 and 1 seconds. We repeated this analysis for other spectral ordinates periods, and the variation is more or less the same. Okay, so this is again the residual analysis that shows the depth dependence of our model. So the first column is normal, the second column is reverse, and the third column is a strike slip. Again, PGA 0.2 seconds and 1 second. And I'm showing the significance of slope term here by simple p-value statistics. Well, I mean, even without p-value statistics, you can see that for normal events and for strike slip events, the estimations, the median estimations, do not show a significant bias for depth variation, whereas for reverse events, we have a significant bias in our estimations, median estimations. Again, this is something related to our
these are event terms, or are these within what do you?
These are event terms.
Event
terms, yeah. Sorry. Okay, so this is the standard deviation, variation of standard deviation. And as you can see, okay, some explanation. Because we developed our model, we derived our model for 3 different distance measures. So here I'm showing the between, within, and total for those 3 different distance metrics. In any case, I mean, there is not too much of difference for different distance metrics here. But essentially, the variation of sigma is almost period independent. But there is some sort of period dependency for periods greater than 3 seconds here, which is much more prominent, visible in within event and total sigma. And the reason for this is that we're using this strict criteria that I and Julian Boehmer set for usable period range, and that criteria essentially chops a lot of recordings after 3 seconds. So because of the, data loss in terms of earthquakes and in terms of axograms for periods greater than 3 seconds, we're observing this drop in total sigma, in sigma. Okay, so as for the conclusions, the magnitude dependence of sigma, so these are actually really addressing or summarizing the questions raised by the project group here. So the magnitude depends of sigma. So the database contains few large magnitude events above magnitude 7. So thus the distribution of data does not allow establishing a magnitude dependent sigma. So our sigma does not depend on sigma magnitude, and the total variation of standard deviation seems to be independent for magnitudes less than 6.5. For magnitudes above 6.5, I mean, the statistics that I showed you, I mean, they may mislead you because we don't have too much data on, for magnitudes over 6.5. The model uncertainty seems to be less significant for magnitudes between 4.5 and 6. This is, I mean, quite strict, but I would say with some sort of tolerance, the upper magnitude limit can raise up to 6.5 and 7. The influence of depth on ASP 13 estimates. Well, the variation of between event residuals in terms of depth indicate that there is there is no bias. The bias is insignificant for normal and strike-slip earthquakes, but there is some sort of bias in our median estimations for reverse events. As the depth increases, our estimations, we are overestimating the ground motions for reverse events. How well the estimates are for different style of faulting, again, our comparisons with the previous NGA West project, NGA West 1 project, indicates that there is a good, say, match with Campbell and Bozorgnia predictive model for normal to strike slip ratios, but and also for the previous Pan-European predictive model, Akkar and Bowman 2010. But there is a significant difference in terms of in our estimations for reverse to strike slip ratio, so which means that our model is doing, well, in our opinion, our model is doing a good job for normal and strike slip estimations, but not for reverse estimations, I would say. All right, so I think I covered all of these points here. Yeah, okay. And reduction in sigma after 3 seconds, as I tried to emphasize, this is something related to the decrease in data size after 3 seconds. So after 3 seconds, because we're chopping too much data because of usable period range, we're observing this drop in sigma. So, all right. These are the references I used for this presentation.
Let's have you run through the other two models, and then we'll take questions on all of them.
All right.